There's some interesting observations. Is that the great red spot appears to diminishing in size. At the beginning of last century, it spanned 40,000 kilometres across, but now it appears only at 16,500 kilometres. So it's obviously shrinking. It's less than half the size. It used to be said that you could get 3 Earths to fit within it, but now it'll only be 1. So hold your breath. The shrinking rate appears to be accelerated by observations indicated that it's now reducing about 580 miles per year. Will it disappear? That picture by Steve, by the way, Steve, one of our astrophotographers. I'll just go back. Fantastic image, Steve. Thank you very much for that. Just shows you how beautiful it is at the moment. Move on. So Venus is going to be near the moon, a very thin crescent moon. So that's on the 10th, so that'll be Friday. So that will be, I'm not sure, I haven't put a time down there, it's a bit remiss of me. But I think that will be in the morning. Okay, so at the moment the constellation of Lyra and Cygnus are almost directly overhead, which is fantastic for astrophotographers because we're going through less atmosphere when we're imaging up here. So it's a point of interest, but I just thought talk a little bit about these constellations. So Cygnus the Swan is a part of what we called the Summer Triangle, the 3 main stars, the bright stars in the sky at that time, Vega, Deneb and Altair. They're obviously going to be disappearing shortly as winter moves on. So I put a little bit of information about Vega, which is an interesting star in Lyra. It's the 5th brightest star in the sky. It's a blue-white star having a magnitude of 0.03 and lies 26 light years away. So it's fairly close. It weighs 3 times more than the Sun. It's 50 times brighter. But it's burning up its nuclear fuel at a greater rate than the Sun. So it will shine for a correspondingly shorter time. Vega is much younger than the Sun, perhaps only a few 100 million years old, and is surrounded by a cold, dark disk of dust, which is an embryonic solar system being formed. Moving on, we're going to stay in the same area. So we're looking at a double star, Epsilon Lyrae, which is just up to the left of Vega. With a pair of binoculars, you can actually see that these are both double stars, and they are called the double-double. So that's certainly something to look at. Quite fantastic when you can actually separate the stars that you can't by eye. Then further on, between Beta and Gamma Lyrae lies a beautiful object called the Ring Nebula. It's the 57th object in Messier's catalogue, the so-called M57. And I've discussed this before, but I'll go through it briefly. It's what we call a planetary nebula, and it was thought to be planets in the past because of the round disk shape, but they're in fact the remnants of stars similar to our Sun that have come to the end of their lives and blown off a shelf of dust and gas around them. The ring looks like a greenish smoke ring in a small telescope. It's not so as impressive as shown in the photograph, but that is one of Hubble's images. So in the centre you can see a white dwarf. That's a remnant of the star, that the material we're looking at, and the solar wind from the star is lighting up all the material. But even with we've taken some images of this, and it comes up really nice if you've got a decent camera and telescope. And then looking at Cygnus the Swan, which is quite easy to spot. It's sometimes called the Northern Cross because it's a very distinctive cross. So we're looking at Deneb, which is the head of the swan, and is well, it looks like the head to us, but it's, according to the Arabic word, they call it the tail. So it depends which way you visualise it. This is a 1.3 magnitude star. and marks the tail of this one. I would have said it was the head, but there you are. What do I know? It's 2,000 light years away and appears so bright that only because it gives off around 80,000 times as much light as our sun. So I put a bit more information there. Deneb is close as the brightest star in the northern sky. Sirius, it would appear as brilliant as half a moon, and sky would never really be dark when it was above the horizon. So that's if that was our star. So there's a little bit picture there of the two different stars there with the colours difference. So one's a red giant and the other one's a blue-white star. So moving down from Cygnus, you're actually looking at the centre of the Milky Way there, the centre of our galaxy. And I'm talking about an area there called the Cygnus Rift, which is a dark area, which I didn't put a picture up of. But just down from the Cygnus Rift is the North American Nebula, and there's a section in the North American Nebula called the Cygnus Wall, which is what you're looking at on that picture there, and this is a star-forming area. I thought that would be quite a nice picture to put in. So if you go along the body of the Swan, about a third along, you come to another nebula called the Crescent Nebula. The Crescent Nebula is a star that's still, it's not a supernova, it's a star that's still burning, but it's burning so hot and so bright that it's expelling all its material and it's lighting it up by its solar wind. So the star is still present. It's what we call a Wolf-Rayet star. But they burn hot, they burn fast, they have very short lives, and this will become a supernova eventually. So I'm going on to some images from our astrophotography section. This is a superb picture by Kevin Noble of the Flying Bat and Squid Nebula. I can't see the flying bat, but I can see the squid, definitely. These are relatively faint nebula in Cephus, but I think he's done a brilliant job there. I really am amazed at the skill and ability of some of our astrophotographers, and Kevin has taken this picture to a new level. Moving on to one of Steve's solar images that he's taken. Again, this was taken from his back garden. So sun last weekend from my back garden, some spectacular flares. So he's using his 100 APO UV IR and UV cut filters. I don't understand because I don't do solar astronomy. But Steve, if you want to talk to Steve about it, I'll explain it all to you. But all I know is that's a fantastic picture. I can just see the prominences there and a sunspot in that top right corner. Another image here. This is from Michael. He's done another picture of Jupiter. Again, he's taken that bit of information 2 nights ago, but these might not have been 2 nights ago because these have been on our website for a while. But certainly in the last couple of weeks. We just haven't had the weather to get some images. This one was taken when 4 of us went to Spain to do some astrophotography. This is one of Steve's M33, or the Triangulum Galaxy, and I think that's a nice clear image. I think you've got the dust lanes and some star building activity going on there, hydrogen alpha. This is one I took in Spain as well. I'm sure you're all familiar with the pillars of creation in the Eagle Nebula. Not quite as good as Hubble's, but you can certainly see the detail there. You can see the pillars of creation there. I've taken the stars out just to give us a better definition within the clouds that are forming, the star-forming clouds in this area here. The last picture in the image is good old Andromeda, which is still nice and clear in the sky. This is one of Steve's images. I put a bit of information, difficult to find different information about Andromeda, but I thought that was quite relevant. Although several dozen minor galaxies lie closer to our Milky Way, the Andromeda Galaxy is the closest large spiral galaxy to ours, including the large and small Magellanic Clouds visible from the Earth's southern hemisphere. Andromeda Galaxy is the brightest external galaxy visible in our night sky. At 2.5 million light years, it's the most distant thing humans can see with an unaided eye. Right, and the only other thing I was just going to briefly mention was that the SpaceX Starship is due to go up next Monday, so keep an eye out for that. It's just a test launch, but hopefully it's going to move the project forward, and it could be one of the most exciting things to happen since we left to go to the moon, I think. Thank you very much.
Thanks very much, Martin. Some amazing pictures, and I always feel that we're so lucky to have people in the society who are actually taking better pictures than those that were published in books when I started being interested in astronomy some time ago. Okay, so we have been associated with the university quite some time, helping out at their Bayfordbury Open evenings. In fact, can I just ask for a quick show of hands? How many of you were there last Friday? That's good. Very good. So we take along some of our own telescopes to cut down on the length of queues that visitors there need to subject themselves to. And we also have a display internally telling people about the society. And it was a couple of years ago that we asked the university if some of their astronomy students would be interested in presenting at one of our meetings, and in fact it went down very well. In fact, we did carefully say we do not want a highly technical presentation. In fact, that's our standard inquiry to all of our speakers. But we do know that the students obviously are investigating their particular subjects in far more detail than most of us know about it. And that is despite the fact that one of them tonight has only been studying here for 5 weeks. So, Shree Mittal is going to talk about an alternative way of thinking about dark matter halos. So I'm sure that most of you have heard of dark matter, but you may not have heard of dark matter halos. So we're going to find out all about it now. Thank you.
Okay, that's fine. Yes. Okay. Good evening, everyone. Thank you very much, and thank you, Jerry, for introducing me. Thank you, Alan, for giving me a very warm welcome. It's my first public talk in UK, so as much as you're going to learn from this, I think I'm going to learn more from this. So, and hopefully it would be beneficial and useful for everyone. Okay, edge of dark matter halos. I decided to give this as the title of the talk because the words are all going to come together as we go through the talk, and why we should care about this, it's going to come together through the talk, and these words are going to make sense through the middle of it. Right. So, before we finally get into the talk, just a simple question. Looking at this image, can you tell which part of the image is the Indian Ocean and which part is the Atlantic Ocean? No, it's impossible, right? So, what I want to say is, nature rarely comes with well-defined boundaries or categories or that can help you identify this is the Indian Ocean, this is the Atlantic Ocean. A very famous example of this exists in the astronomy as well, very controversial, back from 2006, which is when Pluto got redefined from a planet category, which was essentially what is a planet, because nature doesn't have a definition of a planet. It's something that we have to come up with, and based on the definition that the International Astronomical Union came up with, Pluto is no more a planet, which some people are still very angry about. So you can see that how do we say an object is the object that we want to talk about is really difficult when talking about natural objects. So keep that in mind. Now, hold that thought. We are going to look at some pictures now. On the left, what you're seeing is actually made by a computer, and you can see all these web of structure, right? There's all these filaments going out, and there are some very bright objects in the image. This is actually what we call as the cosmic web. This is actually what the universe looks like when we look at it on a very, very large scale. So for example, Andromeda was mentioned. Andromeda from Milky Way is about 0.7 megaparsec away. Megaparsec, just the distance. This box that you're looking at is of 62 megaparsec distance. So that means we are looking at almost 70 times the size, the distance you would for Andromeda. So this is like really on a very, very large scale. Now, this is what the universe looks like. What you see here is actually what we call the dark matter web. And most of the universe is actually filled with dark matter. It's actually 23% of the universe is dark matter. The second thing to notice, a lot of it is empty. The universe is actually very empty. So, what do we call halos? Well, if you look here, there are these very bright, they are actually not bright, it's just because we want to see them, we have colored them, and therefore they look bright. But you can see these very bright objects. These are the objects which are bound, held together, and this is essentially what we call a dark matter halo. Just simple definition, anything which is bound by itself, we will call a dark matter halo. The second thing to know, all known galaxies actually live inside these halos. That is very important. Galaxies cannot exist without dark matter. We will come to that actually. So, a very normal definition that anything which is bound will be dark matter halo. But the question, if I look at an image like this is again a computer, this is not an observational thing, this is just computer generated. Some people might argue that the halo is the red circle, whereas some people might argue it's the white circle. So the question is, where does it actually end and where does the background universe actually exist? Well, we have been talking about dark matter halo, but obviously the question that anyone in the audience can ask, how can you even talk about dark matter halo, because do you even know if dark matter is real? Yes, there is overwhelming evidence that dark matter is actually it's actually a thing, and it's not just a theory that we work on. I'll just gonna discuss two of the evidence that we have, but there's plenty more evidence that confirms that dark matter is actually real. On the right, this is a very famous image called bullet cluster. It's called a bullet cluster because it looks like a bullet. So astronomers aren't very good with naming things, so it's fine. Yeah. So what do we want to see here? And this is in X-ray as well as optical. Both the images are laid on together. What you see is this part of the image. This is the X-ray, and this is very bright. What's happening is these are two very, very massive clusters. So almost 3 times the size of Milky Way. Sorry, it's actually 1,000 times the size of Milky Way, because I'm thinking in log scale. So it's actually 1,000 times the size of Milky Way, two clusters which have collided into each other. So one cluster is ripping through the other one, and as all the gas inside these two clusters comes in contact, it heats up and it starts emitting in X-ray, just very bright. So these are the two gas lobes that you see colliding, which are emitting. But then there are these two blue lobes. Those blue lobes, if you took a telescope, they won't actually appear blue. We have laid it on the image actually, just for easier visual representation. The blue image, surprisingly, is actually where most of the mass of the clusters is. How do we know that? Well, when we look at this image, you will see that the background galaxies are slightly distorted in all the different shapes. So like if you see, these galaxies have a very different distortion compared to galaxies over here. So that is happening simply because as the light travels through the universe and it encounters something which has a lot of mass, it has to go around it. It has to bend in proportion to what the mass is. So from that, we know that there is a lot of mass in these two different lobes. So the gas that we can actually see in X-ray is in the middle of the picture, but most of the mass of the cluster itself is actually displaced. The only way this can happen is if you have something called the dark matter, because we can't see it, so hence dark, but it's still matter because it has gravity in the same way Earth has gravity. The only difference is we can't see it. So the conclusion that you have to draw is there is this massive object that you can't see, but it can, unlike gas, it doesn't bounce. So normal matter, if you drop a ball, it bounces off. However, this matter just passes right through each other. These are the two big differences for dark matter. But this is the only acceptable way that we can explain what is going on in this image. Other people have come up with different ways, but none has been able to explain that image along with all the other evidence that we have. The second evidence, I'm going to try and play the video. This is the earliest way we actually started talking that maybe there is something that we don't understand, back from 1930s actually. So what's happening is, you will see this galaxy, the stars which are especially in the outside of the region of the galaxy are going much faster than they are in this part of the galaxy. Now, when astronomers looked at the galaxy and the stars in our own Milky Way, especially the stars which are much farther out, what they saw was they were going at a much faster rate around the central galaxy than we expect them to. This can only again be explained if you have dark matter, because again, dark matter can't be seen, but it does have gravity. So what it does is, dark matter extends out throughout the galaxy, and because it has gravity, these very far away stars still experience much more gravity than they would in the absence of dark matter. And as you know, the way planets go around the sun, if the sun was heavier, they would go around even faster. So these are the two very well known and very hard to refute evidence that we have that dark matter is indeed something that we can't deny, or we have to come up with an explanation that can explain both of these at the same time, which is very, very hard to do right now. So, dark matter exists because it has gravity. It also clumps together, and these clumps are what we are calling dark matter halo. So we have a dark matter halo, and we want to know how do we exactly know that this is a dark matter halo and this is just background universe. So if we want to ask that question, the obvious reply is going to be, if you can't even see, how are you going to talk about where it ends and where it begins? That question is meaningless. However, we can't see dark matter. What we can see are the galaxies. And every known galaxy actually lives inside a dark matter halo. There hasn't been an evidence of a galaxy up until now which also didn't have a dark matter halo component. So what you're looking on the left here is actually an image taken by a survey which I'm going to discuss, which is what I work on. This is a deep field image, and every point is actually a galaxy, and each of those galaxies actually has a dark matter that we just can't see. I want to take another moment here, and for you to look at this picture carefully and then go back to the picture that you saw of a simulation of the universe. You can see how there are these empty regions and then there are all these connected web. Well, this picture also appears to have the same structure. You have these very bright galaxies, and then you have smaller objects surrounding it, and then there's a lot of empty space. It's not exactly the same, simply because that is 3D, whereas this is 2D on a sky. But you can see the similarities between this actual universe versus the one that we can make in our own computer. And that is actually one of the most remarkable things that we have been able to do, as to how good we are at being able to simulate universe on our own computers actually. And it's actually become a bit of a headache within the science community because we know it's wrong, but everything that we do just gives correct results. So that's a headache. But yeah. Now, so the survey, as I mentioned, it's called Dark Energy Survey. Again, naming conventions are weird in astronomy. Please don't. ask me why exactly is it dark energy survey, but it's called dark energy survey. And that's the survey which took the picture that you saw on the previous slide. This is in Chile, so southern hemisphere, and this is the actual photo from the dome where the telescope is located. You can see a very happy man, and it also gives you an idea of the scale as to how big the telescope is. Surprising actually how chill he is, because it's really galaxy, and once it has fallen, it will bounce back around and then simply start going this very massive cluster, which is very much like a ball on an earth, or the way moon goes around the earth. Actually, it's just that it has not always been there. It caught and then it started going around. So the simple thing to say is, this is just one galaxy, but there can be millions such objects that fall, and not just a galaxy, but anything from something very small to a galaxy. So the simple thing to say is, the very outer point where all such objects turn and finally start going around the object, that is what I'm going to say is where my dark matter halo ends. Anything after that is just background universe. But this boundary, again, we can't see it. We can't see it directly, but we can see the galaxies as they fall and they start going around. So we will be able to see this imaginary line around a galaxy, beyond which, if something actually falls, it never goes out. So that is what we call as the boundary of a halo. Why am I blabbing about this so much? As I said in the beginning, if you want to talk about something, you need to first completely define what this object is. And until unless we have done that, we can't do science with it. At the end of the day, we want to understand the universe. We want to understand why galaxies are the way they are. And in order to ask any of those questions, we have to first answer, but what exactly is the home of a galaxy? So it's very important that we understand that how are we going to talk about it. Now, my work for about past year, more than a year, has been trying to actually find this, because my supervisor, who I used to work with, and she, along with her supervisor, came up with this very nice definition and left the hard work of actually proving that this can be found and can be seen from telescopes onto us. So my work for the past year and a little bit more than a year has been proving that this can be found. Fortunately, yes, I have been able to say that it can be seen, which is great. So this is not just theory anymore, but rather something that you can actually see in the galaxy. I'm not going to go into the technicals of this plot that's here. The only reason I have put it up here is it's just proof that the data that we actually take from all the pictures that comes out from different telescopes and all that goes into doing a little bit of math, and in the end it sort of looks like this. It's not pretty, as good as the pictures. And like I also don't find it that pretty, even though it's my work. But it's just a proof that it can be done. And I've been able to do it. And just for reference, this is about 1 megaparsec. So going back to Andromeda, Andromeda is about 0.7 megaparsec away. So the boundary of a halo, of a dark matter halo, can extend out all the way to Andromeda for something which is 100 times larger than Milky Way. So the galaxy itself is very small because, as we know, Andromeda is almost megaparsec away. So, and we are so far away from it. But the dark matter halo itself, inside which the galaxy actually lives, that can go out all the way to Andromeda. So a galaxy is only a very small fraction of what the universe actually looks like, or what is actually filled with. And that is very surprising result that we found, that the dark matter halos are actually very, very huge objects, much, much larger than the galaxies that we even can see. So, final thing that you would want to take away, the universe is actually a home to a web of all the dark matter structures, and the smallest bound objects are called halos, and every known galaxy actually lives inside this. And asking the question, what is a halo, is actually very complicated, even though it seems simple. But then using all these new telescopes that we have and the ones that are coming up, we are getting very close to answering this question for any size of galaxy, actually, not just the very, very, very large ones. And yes, thank you. Please feel free to ask me any questions, even after the talk. Please.
Thank you. So a lot to get my head around. But you say dark matter clumps, and it's these clumps that is the halo. Now, ordinary matter clumps, and we get stars and planets and stuff.
Yes.
So is that like saying that a dark matter halo is effectively the dark matter equivalent of a star or a planet?
Yes, that's so good of a question. Okay. So this is right now a big debate among scientists as to, can we find objects, because as you said, dark matter clumps. So can we find objects which are star size but entirely made up of dark matter? So right now, the halo would essentially be large enough that a galaxy can live inside it. So these are like very, very large. But can we find something which is almost a planet? So, something like Earth as well is like something that people are fighting about. I think they should be, given everything we know about how this behaves. But yes, we don't have observation proof of this in the way we have for halos. But yes, this is like, people are fighting over this. So yes, that's a very, very
Thank you.
quick question.
No, thank you for the presentation. This is slightly philosophical in a way.
Sure.
I tried to work out whether the explanation you gave with the bounce back
Yes.
dimension of another galaxy,
Yes.
whether that's just the definition of where the halo finishes, or the halo edge is inside it is dark matter, outside isn't. Right. Because that's what I'm trying to work out, whether you're actually trying to define where the dark matter exists
Yes.
and doesn't exist, or just the definition. And the reason why I'm asking is, presumably, the faster a galaxy is moving towards means it'll actually go further out. So I would have thought there would be cases where a very fast moving galaxy could actually go through the halo where the dark matter is, and it's got its own dark matter surrounding it.
Yes.
In fact, the dark matter is outside of your halo definition.
Yes.
So I'll try to work out whether it's actually, you're trying to say that's the edge. So outside of it is nothing, inside is dark matter, or it's just a definition, and you can have dark matter inside or outside of that.
Yes.
Halo.
Thank you. Yes, I think I should have been clearer a bit. So dark matter can exist outside this edge that I have defined as well. It's just that when it exists outside, it's more loose. So for example, imagine the Earth's atmosphere. At what point it stops being an atmosphere is not entirely, because it just, becomes less and less and less dense. The air as you go up just becomes less and less, but it doesn't just go to zero. Even if you go all the way to moon, there's actually still, very, very, very little, but there's still actually, molecules of air, even on the moon from Earth actually, right? So it's not that there is no dark matter outside this definition. It's that whatever object will have this boundary will be definitionally a halo. Dark matter outside of that is just simple dark matter. It's not a halo anymore. So it's really just I'm defining the object halo rather than dark matter. Yeah.
What I think you said was that dark matter exerts a force on baryonic matter.
Yes.
Thank you. Is there any evidence that dark matter has the property of inertia and momentum?
That's a very good question. Okay. So we know that dark matter has mass. We know this because when something has mass, as I said, if light travels through the universe and it encounters something which has mass, it has to bend around it. So we know dark matter has mass because light does bend around it. And mass and inertia are essentially the same in terms of how they behave. They are actually, the same thing. So dark matter does have inertia. It also has momentum. The complicated part is if normal matter, like, what you and I are made up of, like, let's say 2 footballs, when they will be coming together and they have inertia, they have mass, they have momentum, they behave in this very predictable way where they come together and they bounce back simply because of just Newton's physics. For dark matter, everything is same, except if it comes together, it doesn't follow Newton's law where it bounces back, but rather it passes right through. That is the biggest difference. It's also because of this reason that we also can't see it, because it doesn't talk to itself and it doesn't talk to light as well in the way that we understand, which is why it's dark essentially.
Does the distance between the center of a galaxy and the edge of the halo vary with the size of the galaxy?
Yes, very much. So, as I said,
is there any sort of ratio or any mathematical correlation?
No, not that we know of. We know that this is what we know. The larger the dark matter halo is, the heavier it would be. And the heavier the dark matter halo is, the larger the galaxy would be. But we don't have a well-defined correlation for the size of the galaxy and the size of the halo.
Does that imply that the galaxy is attracting more dark matter mass?
It's actually the other way around. it's the dark matter which attracts a lot of this, normal matter that we know into itself, which then lights up to form stars and actual galaxy. So it's the other way around, actually. But you're thinking right.
Any questions for me?
Okay.
Would you like to say what you think the most likely theory for dark matter being correct is?
So we started thinking of dark matter back in the 1930s. As of now, I think the entire astronomy, research, like the entire astronomers agree that dark matter is real. Like it's not a theory anymore, simply a theory anymore. As to what exactly it is, that is a question which has made physicists scratch their head a lot. It's actually very, very frustrating because, okay, before dark matter, physicists had a theory called the Standard Model. It was very good. It is very good. It explains almost everything that we know about the universe, except for dark matter. And we don't know where we are missing. Like we keep trying to throw all the tests that we can so that we can maybe get a new idea. But the theory is so good that it's able to explain everything that we throw at it, except for dark matter. So we know it's a wrong theory. It's incomplete. But we don't know in what ways it is incomplete. And it's very, very frustrating for physicists because we know it's incomplete, but we don't know where to go from here, actually. Yeah.
Well, thank you very much
Yes.
indeed.
Sure.
And I just have one little observation, not a question as such, about what you said at the beginning of your presentation about the IAU's definition of a planet, which I couldn't really let go without mentioning my own presentation on the subject called "Is Pluto a Planet?" And I'm quite happy to tell people that if you follow that definition accurately, then we have only 8 planets in the solar system, because Pluto is most definitely a planet, but Jupiter is not.
Yes.
Which, as I point out, shows what a useless definition it is. Okay. So thank you very much for that presentation. And yeah. So our other main speaker is Will Cooper. How long have you been a student here then?
Yeah, came here in 2014 as an undergrad. And
Okay.
2018 started the PhD.
All right, right.
So I'm a bit more dead behind the eyes than.
So the subject of Will's presentation is characterizing ultra cool dwarfs, right? No, not just cool, but ultra cool. And as detected by the European Space Agency's Gaia mission, which I'm sure you have all heard of. So this is one particular aspect of that mission, which has been so successful in its activities. Over to you.
Thank you. We have presentation. It's on my screen. Have we got it?
Yeah.
There's always technical issues. I always have. There we go. Cool. Right, okay. So yes, characterizing ultra-cool dwarfs in using the European Space Agency's Gaia mission. So I'm a part of that mission. I'm in what's called the Data Processing and Analysis Consortium. That's STEMX. So I work a lot with taking in the data and generating what we call astrophysical parameters based on that. I'll give a kind of broad overview, make sure we're all on the same page. So, computer's turning off. So yeah, Gaia itself launched in December 2013. You may have caught it. The data from a mission is released in these batches. So it started TGAS, I think it was 2017. Then DR2, which is when I joined the scene, was after DR2. And then there was what we called the early data release, DR just stands for data release. And then DR3 itself. So cool kind of diagram. This came out in 2013. So we also now the ground stations, so how we monitor Gaia, because we need to know exactly where it is. The idea is it's behind the moon, in effect. But we also use Goonhilly a lot recently. So if anyone's visited Goonhilly, it's a nice day out. What is Gaia doing? It's observing what we say astrometry and photometry of nearly 2 billion things at once. And the complicated thing it does is it takes some of the biggest supercomputers in Europe at once, and it tries to solve everything at once without assuming anything. So it's enormously complicated maths going into it. It's a lot of fun. I'll talk about just what photometry is. So photo meaning light, metry meaning measure. We want to know how bright is stuff. So this is an image kind of developed from Gaia's data. It doesn't typically image things like you may expect, like through a normal telescope, but it has filters. I think in Martin's thing, you discussed some filters that we're all kind of familiar with. But yeah, Gaia looks in these other optical filters, these G, BP, and RP filters. This one is G, and that's the thing that has 1.8 billion different objects in with measurements. Astrometry, astro meaning star, metry meaning measure. Just going back to the Greek, that's just asking where is everything. So we have RA, right ascension, and then dec for declination. That's simply you take the Earth and you explode it, not literally, but outwards. So it's follow the equator out, and then you can kind of see where things are on this, what we call ecliptic. So it's just a positional thing. Proper motion you then have, which is in those two dimensions, proper motion, right ascension, proper motion, declination. That tells you the kind of direction and how fast something is moving. So the very, very accurate measurements is the main thing. I've heard it said that Gaia could observe from the moon the rate of change of someone's hair growing. So kind of scale that up. Diagram you may have seen. It's not as scary as it sounds. It's a combination of photometry and astrometry. All it's saying really is to the left, things get kind of hotter, and as you go up, things get brighter. It's what we use to classify things. It's called the Hertzsprung-Russell diagram. Been around for decades now. So I've split that into three. So you actually get three components of the galaxy. I'm not going to go into your dark matter stuff because I don't understand that. But there's different classes of objects. You get your white dwarfs living down here. Like they're not very bright, but they are pretty hot. You've got your main sequence of dwarfs, a strong band in the middle. You then have, I can't reach that high, but you have subgiants going into giants. That's when a star has run out of fuel. And unnecessary. Thank you. Yeah, here we go. Subgiants, giants, supergiants, hypergiants. Again, imaginative naming scheme. And just under this dwarf kind of sequence, you get what we call subdwarfs. So a bit smaller, a bit bluer. So yeah, three components of a galaxy, what we call the thin disk. So that's the main thing that you could see kind of along here. That's your thin disk. Thick disk, things are a bit older. Yeah, just they've come out of that plane a bit. And then halo, so separate to the dark matter halo, is things even further out, tend to be older. We basically take velocity or speed of something as a measure of how old something is, because they correlate. And that's just, I find it actually quite cool. But over time, you get small disturbances in something's motion. So you start chilling on its own, another one comes by. Yeah, and this is so unlikely, it takes millions and billions of years. But by the time you have something which is billions of years old, it's been sped up by those interactions until you can actually say, well, that must be my halo, ergo an old object. Okay, stars. I think we know what stars are, but I like the picture. So, hot ball of stuff, hot ball of plasma. We say it burns hydrogen. Again, Martin, you covered this as well quite well. But you have what we call nuclear burning instead of chemical burning. So it's not a fire, it's explosions, it's just explosions. So those stars are what we see in your kind of main bit. The things that I'm interested in are what happens when you go cooler than that. Because there is a ignition point of hydrogen within the center of a star, about 13 million degrees, pretty hot. So actually much hotter than the outside. So the sun, for example, just shy of 6,000 degrees. But I want to know, when you go cooler than that, what do things look like? So we have the sun, go about 6,000 degrees. We say K, that's Kelvin, instead of Celsius or Fahrenheit. And we got these new classifications that we made up. And the first one of these was made in the late 90s, where we said, actually, there's things dimmer than what we've detected before. We need to come up with a naming scheme. So there was an acronym people may have been familiar with, OBA FGKM, OBA Fine Girl Kiss Me. I don't think we're actually allowed to teach that one anymore, but no one's come up with an alternative. Anyway, after that, after those M's, we also needed these L, T, they came on in early noughties, and then Y. So the pre-definite paper that defined a Y dwarf, which are things which can be coffee temperature objects, down to room temperature objects, those came from about 2011 onwards. So we defined an optical dwarf as anything less than 2,700 degrees. So, the kind of a temperature you're working with, like iron kind of smelting, So what are those? Well, what we call low mass stars. So your kind of red dwarfs, TV show, brown dwarfs, which are kind of our specialty, and exoplanets. And they're all fairly similar sizes, so physical sizes to Jupiter, even though there's a lot more mass in there. We'll focus on brown dwarfs because University of Hertfordshire is actually one of the main centres in the world for brown dwarf research, has been since it's kind of created. So some objects can do what we call burning deuterium instead, so heavy water. And that supply doesn't last very long, so it runs out. And then, like all the other brown dwarf planets, it just cools down over time. So they've got no real life cycle. They're just born quite hot. So it might be like a late M dwarf, as we would say. And then it cools over billions of years into L, T, and then Y. And you can tell things get more technical because the graphs get uglier. So here it's just how old something is. So this is a baby, just 1 million years old. And then that's how bright something is. So it goes dimmer over time to the end there, which is about the age of the universe. Okay. My main focus is on spectroscopy. So rather than just, photometry, where we're taking images and analyzing how bright something is, we spread it out like you would with a prism, and it makes the rainbow thing. That's exactly what we're doing with slightly more precise equipment. So again, M, L, T are your blue, dark blue brownish and red, not great at colours. I have Jupiter at the bottom. So you may see some bits missing, and that's because the Earth's atmosphere itself gets in the way. And that's the reason we're so excited about things like JWST, because it's in space. We don't need to worry about the Earth's atmosphere. So we can fill in those gaps and get much better data, because it is the most awkward thing to deal with, the Earth's atmosphere. Spectral suite, I will also have an aside, is for one word that I've covered so far, which is a combination of Latin and Greek roots, which really actually does bother me. But yeah, this is how we classify most stars in general, are what features are present. So if anyone can remember kind of secondary school chemistry, you may recognize some symbols. You've got your methanes and your ammonians, waters, and iron hydride, for example. And we use those to tell us what exactly type it is. So within those bigger spectral types, like M, you'll have M1 through 8, and then, M9 as well. K goes to 8. No reason. L as well, kind of 0 to 10 effect. And these are just subdivisions in what features are present in the atmosphere because of different temperatures. So, yeah, you get things like iron in the atmosphere, which disappears at colder things, that kind of thing. Cool. So, what do I do? So, Gaia, I say it just as astrometry and photometry, it also does spectra. And it does spectra in a very weird way compared to how we traditionally do spectra. And that, as Shree had a CCD, which you should be familiar with from like your cameras, anything you've used before. So Gaia actually monitors as something moves across, because Gaia is spinning. So it monitors as it moves across the CCD. And we use that, some really horrific maths again, and then you get these kind of curves. So you may spot the difference, kind of nothing alike. So you can't see spectral features, but you can make a spectral sequence. So very low resolution is what we mean by kind of all these things get blurred out. It contains what we call a response function, which is just how the CCD behaves. If any of you have taken kind of like dark current, things like that, same kind of concept. And one of the main issues is because Gaia is in the optical, it's not super complete for optical dwarfs. And that's because most of the optical dwarfs flux, or where it's brightest, is looking at infrared, so the warmth of something as opposed to visible light. So what was my job? So my job was to say, what is a normal object, first of all? So come up with a definition for each optical dwarf kind of subtype, as we would say. What's the standard? What should it look like? Because from there we can start having a look. Velocities again in the different directions in the galaxy. So U, V, and W, we call them. Doesn't really matter. But the things outside that, the second dashed line, those are in the halo. And between the middle, that's a thick disk. Whereas everything else kind of normal should be within that middle ellipse in the middle. Okay, so it shouldn't be moving very quickly. These ones out here, considering how close they are, so everything that I'm working on with is in about 30 parsecs, because they're just that dim, that's as far as we can see. So it's good news. Despite the really, really conservative selection, I'm still getting the most extreme object. There were 2 out of these 94,000 things that were new detections. that passed all, some further restrictive checks. And they're kind of highlighted, the ones without blue circles. So these are interesting objects because they're subdwarfs. The subdwarfs meaning they're going to be old. So that's still one of the mysteries, is how did those things get that old and be so close to us? So what's next from this? So this was just a kind of proof of concept kind of work. So the thing I'm doing now is current buzzword, machine learning, AI. Let's make a computer do the hard work for us, do stuff a bit cleverer. So here we are looking at photometry again. So it's now data points instead of nice pictures. But again, it's just hotter or bluer and then brighter. And those kind of boxes are where things typically exist. A blue box if it's a subdwarf, something old, and a magenta box if it's something which is probably young, because young things are also exciting. Okay, what else do I do with these objects? So we found some interesting things. Let's go confirm what they actually are. So we do what's called spectroscopic follow-up. Step 1, you find your interesting targets. Step 2, you imply, which you do about once a year to all the different telescopes. Super competitive. You can imagine the oversubscription rate for all the big telescopes is minimum 4 to 1, 5 to 1, 6 to 1. And you're competing with a lot of other good science from every other field as well. You work out then, if you actually manage to get time, the specifics of when. So when in the night is it going to be in the right position? A lot of you may have had to do this for astrophotography reasons, and what you can observe. So I may have a list of things across the entire sky, but if I've got all my targets in the northern hemisphere, and then in the southern hemisphere is where I've got a telescope, you can't do a fat lot. Okay. Then you do the fun bit, observing. So you get to either remote observe, which is really awkward time zones that you have to consider. So for example, when I've been observing for Hawaii from Hatfield, not as nice. You have to get up at 4 a.m. kind of thing, do the 12 hours kind of observing, and then finish up the night there. So you have to be really careful you're doing the step 3 correctly for what's visible. You, of course, even in places like Hawaii, nights get cancelled. So I had a night recently that got cancelled in Mauna Kea, just because, actually it wasn't recent, it was a couple of years ago. But there was a volcanic eruption. So that doesn't bother us here in Hatfield, but in places like Hawaii, it happens. And then final bit is you process that data. So as you may do with your maximum DLs and your solariums, you do your stacking of images or equivalent fix for the Earth's atmosphere, if that's of interest. And anything that you can do to take raw images into nice data. Okay, so these 2 images, if you don't recognize them, so this one is the GTC, where the rest of my plots are going to be data from. So that's in Spain. So Shree had the biggest lens. I've got the biggest mirror. Not the competing, but that was a 10.4 meter mirror. So it's currently the biggest telescope in the world. Much bigger ones are being built though. Again in Chile. And we have one RTF, so the infrared telescope facility in, again, Hawaii, top of Mauna Kea. It's really good for doing our infrared observations. Is that me? Yes. Okay. Okay, so we take that data. We then can look at the features and we take measurements. Or you compare to a standard library of similar ones which have already been done. The main thing I want to get across here is, in astronomy, it's very hard to be absolute. There's no such thing as getting the same measurement, even with the same piece of equipment, if it's on a different night. Because it changes night by night, it changes instrument to instrument, and it's just a nightmare to cross-compare. So we do everything on a relative scale in astronomy. So for example, you will make a library from one telescope done as best as you can, and then the spectral typing to say what subtype is it. Is this M, L, or T? Is this 1, 2, or 3? Within that, you go through that standard library and you just see what fits best, what looks best. And then you say that's the spectral type of this object as well. So this object was actually my best behaving one. And you can see, so the black one is my one that I did with some modern software. The orange one is a colleague of mine did with some older software, the kind of standard in the astronomical literature. That's been around since about the 60s and 70s, this bit of code. And then the blue one is the same object observed with a different telescope on a completely different night. You can see they're all different, right? Slightly, in important places, such as these dashed lines, which are, again, are molecules and features that we're looking for. Okay, what do I care about? So, as my role in Gaia is doing the astrophysical parameters. So that's the temperatures, so I want to know how hot the stuff is. Surface gravity, so what's literally the gravity on the surface of the object. So typical for brown dwarfs, it's 5 compared to the sun, which is about 4.4, and that's in log scale. So all I'm saying is brown dwarfs are a lot more dense than the sun. And then metallicity. You've got the standard thing with astronomers, like we talk about features and elements, but at the end of the day, everything that's not hydrogen or helium is a metal. So we just want metallicity. So that again they're quite important features, surface gravity and metallicity. They're telling us about ages, anything like that. And we really care about age. Because going back to the brown dwarfs thing, the thing that's impossible, or really hard to separate, is mass and age. Whereas with normal stars, you can actually tell independently ages and masses, just based on how bright they are. Brown dwarfs, because they're slowly cooling over time, you have no idea what time it is that you've observed them. So therefore, what's the mass? And that's the thing we care about the most. Cool. So, what else looking at? So the features themselves, zooming in. So this is typically how things were defined in the first place for, what are standards. And I know they look like squiggles, but they are important, what we call like alkali lines in this case, so our metals. So sodium, for example, our NaI, is a doublet because there's two things next to each other. That's just the effect sodium has on the atmosphere of a brown dwarf, and that's highly correlated with the age of something. So the deeper it is, the kind of older it is. And it's that kind of concept of how broad a feature is, how deep it is. That's what we're most interested in. What else do I care about? Well, I want kinematics, right? I want my full astrometry. So I know from Gaia its position, RA and dec. I know its proper motion, so that's as it moves on the sky for us. But I also want radial velocity. So that's the line of sight velocity, so as I'm looking at it. So you may have heard of like blue and redshift. It's the exact same thing. So I want to know from that completes what we call 60 kind of kinematics for where something is. And if I know that, I can bind it to other groups. So I may find something, this is a young moving group, so it will be full of lots and lots of stars that we already know the ages of. And if I can say kinematically that my brown dwarf, which I don't know the age of, is in that group, I can just use the age of the others. And from there, I can get the masses out. And then we know everything for it. So this is kind of that bit of analysis. So again, from the same bit of work I've highlighted here. Again, you just got your bluer things and then your hotter things. But in effect, these are the cooling tracks plotted on where normal objects sit. Those are those grey points. And then the objects I had observed are kind of scattered around there. So younger things, as you come up to here, so you can see that top line, I'm saying it's 10 million years old. And the bottom here is your kind of typical, what we call field age, which is 1 to 10 billion years. there isn't actually, as you can tell, a fat lot of difference in something that's 1 billion or 10 billion. But there is a lot of difference between 10 million and 100 million. So we're just taking all the data that we've gathered, all the astrometry, all the photometry, all the spectra, all the information we get from that, seeing what we know about these objects. And that lets us do population statistics, which is the most interesting thing in astronomy, of how does this population behave as a whole. So, something else I've been working on. So there's a group working out of Flatiron in America, and I've been building this website for them, where it's basically a Google for optical dwarfs. So you can search by a ton of different ways, and it's just all the kinds of different data that we want in there. Again, open source, feel free to use it. If you want anything, if you want data, if you want to download Spectra for yourself, this is a good way of using it. And the final bit of advertising is this thing called Backyard Worlds. So this is a citizen science project, which means we want you involved. So anyone that has any free time whatsoever, we want you to look through some images. So taken with the WISE satellite, which is looking at infrared where optical dwarfs are the best. And it's called for the search for Planet 9. Because again, Pluto's not a planet. And as part of that, you'll be put on these papers where we have, a citizen has said this is an interesting object. We've then gone ahead and observed it, done a analysis and gone, yes, this is an interesting one. Yeah, so this is one recently that I was on observing it that was something kind of nearby that just came out of this search, and that's I don't say normal person, but someone with an actual job that isn't astronomy has gone and found that for us. I've left a link there, but please, if anyone's interested in getting involved, that would be really, really great. Okay, and that's all I wanted to say. Right?
Thank you very much, Will.
Yeah.
Do we have any questions from the audience? Okay.
I might send you that link afterwards as well.
Just for my own understanding of where this fits in with all the other stars, is there actually a rough calculation for how many of the small objects you're looking at compared to, say, sun-sized objects? I tried to get the ratio. Is it 10 times? Because my assumption is the smaller there is, the more of them there are. So it's just, is there actually a rough ratio for how many brown dwarfs there are compared to sun-sized objects?
And it's actually one of the most fun bits of research recently is you've got these things called the initial mass function, where exactly as you're saying, as things get smaller, they're easier to make, so there's more of them. Hey. But we're actually finding when you get down to the kind of brown dwarf masses, it goes down again in some of these bins like your L and T, mostly in the T. And the question is, have we just not got enough observations? So are we just missing a ton? Because again, we've only in this past kind of decade that we've really picked up the actual number. Or is something going on in star formation? Which it can be, because there is a kind of debate on how do brown dwarfs form. Do they form like planets, which is kind of in a disk, after a star is already kind of ignited? Or are they forming like stars themselves? The answer is both to some degree, but we are trying to work out that degree. But you're absolutely right, that's a really interesting thing we're trying to find out. But there are typically more. So M dwarfs are the most numerous thing.
Any other questions?
Something I'd like to ask is among these ultra-cool dwarfs that you've studied so far, have you been able to determine from their proper motion whether they've got any sizable satellites? I mean, like, for instance, are any of them double or triple systems, or have they got substantial planet-sized satellites?
Yeah, absolutely. It's another actually fascinating point of research at the moment is what we call the binary fraction. So we know for the hottest stars, they've got quite a high binary fraction. Like most O-type stars are in binaries. There's a common thing that is said that 3 out of every 2 stars are binaries. That same thing holds down to stars. But ultra-cool dwarfs, that number does drop as you expect. But again, we're trying to fill out those, what we call bins, so like the L, T, and Y, to really know, okay, how many of these in binaries? Because they're so dim, it's so hard to actually measure, are there 2 objects? Is there just an object behind it? It's a third object. And this is a constantly evolving field. For example, the definition of what we call L3 is a system called Kelu-1, where it's literally the definition of a spectral template, but it turns out it's actually a binary system, and then it turns out again it might actually be a trinary system. So it keeps going like that. So the answer is we're working on it, but sure. Yeah, sure. But it is really interesting, yeah.
Any others? Any questions on the
Right, well, thank you very much, Will, for the presentation and for answering the questions here. So once again, in fact, as shown by the questions, we've had 2 really interesting presentations today, and we really do appreciate it. And I mean, what else can we say other than we're looking forward to next year's? So I'm now going to hand back to Alan, who's going to tidy things up for us.
Okay, thank you, Jerry. Can I just repeat those thanks to our speakers for coming along tonight? There were 2 fantastic talks, and we wish you every success with your continued studies. I've got a few announcements. The first one is, after our last meeting, this coat was left behind. If anyone recognises it, I did call the university, I did send emails out. It's got a pair of glasses in the pocket, so I'd have thought somebody would have recognised it by now, but nobody recognised it. I'll leave it with reception otherwise. Okay, we've tried. All I can guess is it must have been here when we arrived last time. Okay, so here are a few dates for you. As I said, they will all be on the website, but to give you early warning should be good. The first one is December the 1st, is the next Bayfordbury Open Evening. It was lovely to meet some of you there, and it's a good introduction to our club to have representatives at that event. If you've got a telescope and want to bring it along, we can set it up down by the domes, of course, if it's clear, that is. And we did have a lovely clear night Friday. But it's always good, and the people we get coming to look through the telescopes are very impressed with what they can see from, compared to the universities. Ours are relatively inexpensive telescopes. They're still quite expensive, some of them, but when we tell them that a £70 one from Lidl's will actually show you the same things, and they're quite amazed. That's December the 1st. The Institute of Physics next talk, it's not about astronomy, but it's about how MRI reveals hearing damage and other secrets of the brain. Suffering from a bit of hearing loss myself, that might be a good one to go to. December the 6th, that one. On December the 7th, Thursday, is the next Hagas meeting. our astrophotography group. They're having a meeting. Patrick Cosgrove is going to give the talk. Now, you've seen some of the wonderful photographs from Martin's presentation. It would be amazing, I think, if we could look at the sky and see these objects for ourselves. If our eyes were capable of doing that, I think we'd probably find the sky was just absolutely chock-a-block of things that we just don't normally see. But the cameras reveal it. And I think that is the wonder. It's almost alchemy, isn't it? How they can point a camera into a dark bit of sky and suddenly they're talking about nebula and galaxies and the invisible universe. So if you want to get started on that, members of our club, those paid up members, you can go along and enjoy learning about how to connect a camera to your telescope. Absolutely fantastic. And the final announcement is December the 13th is our next meeting here. Now we're going to have to make a little bit of a change because the speaker we'd got booked can't do it. So we will send out details of the replacement once they're known. We'll get those details again on the website. So all that needs to be said now is very many thanks, first of all, to our technical team. Can I say to those of you on Zoom, I'm sorry we had a couple of problems, but if you did miss the gap there, get the catch up as we put it onto YouTube. Should be there by about Saturday. We've got a question from the audience. Dennis? Yeah, I should have said that. The Haggas meeting isn't here. It's at the Stanboroughs Club in Hoddesdon. Okay. Again, the details and directions will be on the website. Thank you very much indeed. So thank you very much indeed to all the technical team, all the other committee members who've made tonight possible. Again, thanks to the speakers, but more especially, thank you to everybody who joined us for the meeting tonight, either in the university or on Zoom. Those of you in the university may have a safe journey home, and we look forward to seeing you some other time. Thank you very much and good night.